Okay, so the next speaker for today is Robin Marzucca from Durham. He will talk about numerical evaluation of elliptic polylogarithms. So without further ado, please go ahead. I'll switch off my...
Yes, thank you. Thank you to the organizers for setting up this conference and also for inviting me to present my recent work here. So today, again, we're going to talk about numerical evaluation of elliptic polylogs. And for me, the motivation is exactly the same, namely that and despite all the, we have made a lot of great progress in terms of Feynman integrals that contain elliptic sectors. But at the end of the day, at some point, we do want to get numbers out of those in order to do some phenomenological studies. And for this, we need a way to extract these numbers, and ideally, this will be an efficient algorithm. So let me just briefly set the stage. So these are the elliptic polylogs I will be talking about. So these gamma tilde functions, which most of you have seen many times before, already this week and before as well, probably. And they're defined as iterated integrals over these functions Gn. And these functions Gn, they are the expansion coefficients of the Kronecker-Eisenstein series F, which is seen here, which is defined as a ratio of Jacobi theta functions. And the Jacobi theta functions, we've heard this already yesterday from Stefan. There are many conventions, different conventions for these, and this is the one we used, although I believe it probably doesn't really matter too much. Anyway, so we see here already that so we have this sign of 2n plus 1 pi z. So this f is periodic in z, obviously, and if you take the ratio, you'll find that it is also quasi-periodic in shifts in tau, which means that if you shift your argument z by tau, you'll get this exponential e to the minus 2 pi I alpha multiplying the Kronecker-Eisenstein series evaluated at z. And of course, these properties translate also to the expansion coefficients, so to these GNs, meaning that, again, this Gn of z plus 1 is equal to Gn of z, and Gn of z plus tau, you can essentially get a shift where you get a sum of different of these expansion coefficients. Okay, now, as I said, many computations have been done in the literature using elliptic polylogs. And in cases where they depend only on tau, there are actually means to get a number out of them, which is that you can transform them to iterated integrals of modular forms, which you can then Q expand. And then this Q expansion you can evaluate numerically. And this has been done by many people before, and I've certainly not managed to find all of them, so there's some few dots here. And our goal is to in the end, to find something similar for elliptic polylogs. First, I'll go a little bit into modular forms. So modular form is essentially a function that behaves nicely under these modular transformations, so transformations in SL2Z. And when I say behaves nicely, what I mean is the following. So a modular form f of weight n is, first of all, is a holomorphic function. It is holomorphic as tau goes to I infinity, and it behaves in the following way under modular transformations. So you get this factor c tau plus d to the power of n, and this n here is the weight of the modular form. And then they are related to the elliptic integrals that I'm considering, namely if you have an EMPL evaluated at a rational point. And by this I mean that the argument z and all the zi's, they are of the form a plus b tau, where a and b are rational numbers. And in this, if we have an EMPL of this form, then we can rewrite it in terms of iterated Eisenstein integrals. And we can do this using the coaction, and I'll be very brief here because this will not be the main topic of my talk. Obviously, if two functions are the same, then their coaction must be the same either. And the coaction of an elliptic multiple polylog can be cast in this form. So you get a sum over tensor products, the first entry of which can be written again as an elliptic multiple polylogarithm. And the second entry can be cast as a word of one forms, and in particular one forms that contain this Kronecker-Eisenstein coefficient. Right, so if we want to rewrite this in terms of iterated Eisenstein integrals, we'll notice that, and this is where the rational points come in, these Kronecker-Eisenstein coefficients can be written in terms of these functions h, which are the Eisenstein series. And these are modular forms, okay? So then what you'll have to do is you take the coproduct of an EMPL and you apply this function which extracts the cusp value at I infinity from the first factor and integrates the word of one form. So you get an iterated integral, which is exactly an iterated integral of Eisenstein series in this case. And these functions, they can be evaluated numerically by computing the Q expansion. And this has been done many times before. And now we're gonna have a look at how we can do something similar just on elliptic multiple polylogarithms. So let's come to this. First of all, so our goal is to find a series expansion of an EMPL that has three properties. First of all, it should be well defined. Second of all, the convergence should be quick because we may want to evaluate this to high precisions. And then lastly, obviously, we also want to be able to evaluate the expansion coefficients. Otherwise, all of this is no use. So these are the types of elliptic polylogs we're going to look at from now on. So the integral from 0 to z will always consider the straight line. And we want all the EMPLs that we consider to be well defined. Now, what I mean by that is the following. So you know that these Kronecker-Eisenstein coefficients, they can have poles at these lattice points of the lattice defined by tau. For n larger than 1, there's no poles on the real axis, but for n equals to 1, you can also find poles on the real axis. And when we say the elliptic multiple polylog should be well defined, that means that we only consider EMPLs where z is such that there are no poles between 0 and z, so on the straight line between 0 and z. First of all, obviously, if the endpoint is on a pole, then the integral diverges. And second of all, if you have a pole somewhere in the middle on this line, you can regularize this by integrating around the pole, but then of course, depending on which way you deform the contour, you will get different values. So this is something that the user will have to deal with beforehand. Okay, now these coefficients, G, they can be formally expanded as a Q series, where Q is defined as e to the 2 pi I tau. And the expansion looks something like this, which you may or may not have seen before, but you probably have. And of course, if tau is in the upper half plane, if the imaginary part of tau is larger than 0, that means that the modulus of Q is smaller than 1, which in turn means, well, which is a good sign for this thing to converge. However, we also have this dependence on z here, which is also a complex number. So we'll have to be a little more careful, so, because the convergence of this series also depends on the value z. So the first thing, right, so if we consider this recursion for the elliptic multiple polylogarithm, we have this integral where z prime g of z prime minus z1. So this must mean that these the series expansion of the Q series of these G's must converge on the whole range from 0 to Z on the whole straight line. And then we can go and perform the expansion and then do the integration afterwards. So the first step of our algorithm is to prepare the elliptic multiple polylogarithm. So first of all, this is the easiest step. We want to use the quasi-periodicity of these Kronecker-Eisenstein coefficients to shift all the Zi to the fundamental domain, which we call it, which is not to be confused with the fundamental domain of SL2Z, which is just defined by this fundamental parallelogram. Okay, so this is straightforward. So we have a little example. Here, let's assume Z1 is already in this in d tau. Then here we can shift the integer values just for free, essentially. And then when we shift this tau, we get the quasi-periodicity kicks in and we get a term, a sum of two terms, first of which has a 2 pi I here. Okay, so that was step one. Now, step two is to regularize the EMPLs, which have 1, 0 as their last argument in here. Because, of course, these will formally diverge. They have a singularity at z equals to 0, so at the starting point of the integration, which we don't want. So, and we've also seen this in talks before, so we can regularize these EMPLs using shuffle relations, which means that we can write them as a polynomial in these gamma tilde 1, 0 z tau, where all the coefficients of this polynomial are finite and well defined for z equal to tau. Again, so I've picked the example, this gamma tilde, which we've, and the gamma tilde 1, 0 z tau, you can regularize, well, in principle, as you like. So we chose this form here. I believe we've seen a different form in a talk yesterday. And here's the example. So this is the EMPL we saw in the previous example, which has a 1, 0 here in the back. So you can use shuffle relations to write it in this form. And now all of these EMPLs are regularized and finite for z going to 0. Okay, so at this point, all of our EMPLs are well defined, and we can start to think about the convergence of the Q series. But it is very important to first regularize them before the next step, because otherwise you might get some wrong results. So step 3 is to optimize the convergence. What does that mean? So as we've seen before, the convergence of the Q series depends on this modulus of Q. And at least since tau is in the upper half plane, we have that Q is much smaller than, that the modulus of Q is much smaller than 1 and depends on this imaginary part of tau. However, if you just, I mean, being in the upper half plane doesn't mean too much, because the imaginary part of tau can in principle become as small as it wants. So luckily, we can use modular transformations to shift any tau in the upper half plane into the fundamental domain of SL2C, which is this shaded area up here, which continues on to I infinity. And of course, once you've done this, then the smallest imaginary part you can possibly get is here at this edge down here. So imaginary part of tau will always be at least square root of 3 over 2, which means that the modulus of Q will be smaller than 0.004, roughly. So this is very good for the convergence of the Q series. Now, this is step 3, so we optimize tau, which means we map it to the fundamental domain. And to do this, we have to use the properties again of these Kronecker-Eisenstein coefficients. So under modular transformations, they transform, as you can see here. And we can use this to take an EMPL evaluated at a tau, which is not in the fundamental domain and rewrite it as an EMPL, which is in the fundamental domain. So you have a simple example again, because these things can get quite messy, but so we have let's assume that tau is in the fundamental domain, then obviously -1 over tau is not. So and then we can rewrite this EMPL as a linear combination of these two terms. Okay, very good. So now we've got something which in principle will converge quickly. However, the step 3, so the mapping to the fundamental domain, does not necessarily commute with the first 2 steps that we've taken, which means that at this point we'll have to start again at step 1 and go through these 2 steps again. This is, however, not too much of a problem because these steps are usually pretty quick. Okay, once we've done that, we come to step 4, which is to prepare the argument z, so the upper integration boundary. And in particular, we want z to be in this, well, half of the fundamental domain d tau. We call this d tau prime. And this can be easily done as well. So first of all, if z lies in the lower half plane, then we can use reflection identities of these g's. So we can use parity to rewrite the EMPL as an EMPL of -z. So then z is somewhere in the upper half plane. And then we can use path decomposition to split this path, this integration path, along, for example, the intersection points with the lattice defined by tau, and then shift all the integrations, and then shift all the EMPLs that we get from this path decomposition, such that they're again defined as integrals from 0 to psi I plus 1 minus psi I. Okay, and again, I have a little example. So this EMPL N1Z, 1Z can be, we can decompose the path such that we have an integral from 0 to psi 1 and an integral from 0 to z minus psi 1, where again, we have shifted the argument z1 here as well when redefining the integration. And of course, then now this z1 minus psi 1 does not necessarily lie in this in the fundamental domain d tau anymore. So for the very last time, we'll have to go back to step 1. Okay, now once we're through the first steps again, we finally have an expression in terms of elliptic polylogs that are ripe to be expanded. So this is step 5. We're going to compute the Q series. Okay, so we have an expression in terms of EMPLs which are well defined and where the Q expansion converges on the whole path of integration. So this means that we can now expand the integrand and then integrate the different coefficients of the expansion separately. Now, what do these coefficients look like? Obviously, they're also going to be iterated integrals, and they're going to be iterated integrals of this form. So we have this function f here, which consists of these terms. So these trigonometric functions, which are exactly the functions we've seen in the Q expansion of the Kronecker-Eisenstein coefficients. Now, in order to perform these integrations, what we want to do is we want to change variables from these sigma i's to psi I to chi I, which is defined as e to the 2 pi I sigma I, and we're going to call e to the 2 pi I z I wi, and e to the 2 pi I z we're going to call w. You know, what we get is an iterated integral, this time from 1 to w of some function g, where now the function is a product of terms of this form. And now, of course, these are rational functions, right? So we know that these iterated integrals will evaluate to regular multiple polylogarithms. So this is good because obviously we want a Q expansion that we can evaluate afterwards. So, and from now on, I'm gonna talk a bit about this transformation. I'm gonna call this everything that happens here Z space, and everything that happens here I'm gonna call W space. So yes, we get multiple polylogarithms. So there's one more subtlety in this step, which is however crucial. So we switch from this integration in Z space from 0 to Z to an integration in W space going from 1 to W. However, the integrals, they can have logarithmic branch cuts, right? So we can have simple poles in the integrand. So what happens is in Z space, we have this integration on this straight line, which in W space gets mapped to this blue curve here. And this pole Z1 here gets mapped to this pole W1. So clearly we can't just integrate on the straight line path in W space, because then we would pick up a residue here that we need to consider. Now we can solve this problem by doing the following. If we take these poles Z1 and Z2 and draw these blue lines, which are just parallel to the imaginary axis, and then we compute these intersection points Z tilde of the original integration path with the blue lines, then all of this is mapped in W space to this curve. And if we integrate along this orange line here, so to W1 tilde and W2 tilde and then to W, we ensure that we're always crossing the path on the correct side of this pole, because these blue lines get mapped to essentially the angles under which we find the pole, and this way we are always on the correct side of the pole on a specific angle. Okay, very good. So now we've got an algorithm that can do that we can use to expand elliptic polylogs, and now we come to some applications of this. One of the applications is the banana diagram, which has been considered by quite a lot of people already as well. I think some of which are here in the audience. And in particular, we're going to consider the equal mass case of the banana diagram. So this corresponds to an integral family defined here. So we get the A1 to A4 are the exponents of the 4 propagators, and we want to integrate this over 3 loop momenta. And this integral family has well, 3 master integrals, 4 if you count the tadpole, which we can normalize to 1. And these are the 4 master integrals we chose in our paper when we computed these integrals. And we defined x to be the ratio minus 4m squared over p squared. And since all 3 of these integrals are finite in 2 dimensions, we are going to consider these integrals for epsilon equal to 0. And we have computed these integrals first in terms of iterated Eisenstein integrals, or iterated integrals of modular forms, which we have then transformed to an expression in terms of elliptic multiple polylogarithms using the algorithm that I described before. And now I went and took the expression of the master integrals that we obtained in terms of elliptic polylogs and evaluated it numerically using the algorithm that I just described. And so for one, we evaluated it for some ratio minus p squared over m squared equals to 100. And I computed the first 100 digits. Well, I'm showing you the first 100 digits of the 3 master integrals at this value, which of course we could cross-check using the expression in terms of iterated Eisenstein integrals that we had. Yeah, so this worked pretty nicely. Then I also went and made some plots for the 3 master integrals, which are horribly labeled. Okay, so this is the integral I1, this is I2, and this is I3. And I plotted them from minus p squared over m squared from 0.1 to 1000. Okay, so I plotted the inverse, as you can see, but this is what they look like. And in order to make these plots, actually, I used a property of the output of our algorithm, which is quite nice, namely that you can compute an expansion and reuse it to a certain degree. So in principle, you can do this expansion up to the path decomposition of along these orange line bits. And as long as that remains in this fundamental domain d tau, you can actually reuse your expansion as many times as you want. So I actually only had to compute one expansion, and then just I was able to make the whole plots here. So this is obviously very nice if you want to evaluate your result at multiple phase space points. And then lastly, now I want to go back to this relation between EMPLs at rational points and iterated integrals of modular forms. So to write an elliptic multiple polylogarithm at rational points as an integral of modular forms, I've showed you before, you have to apply this map, which computes the cusp value of the first entry, which is an elliptic multiple polylog, and integrates the second one. And of course, the cusp value at I infinity corresponds to the leading term of the Q expansion that we're computing. So that's another, I think, quite useful application of our algorithm. Yeah, so this would be the algorithm. We've found a Q expansion of EMPLs. The algorithm, or the convergence of the algorithm, is optimized to some degree at least. I don't know if there's any other things you can play there, but at least mapping tau to the fundamental domain optimizes the convergence in some way. We get coefficients which can be cast in terms of multiple polylogs, so we can evaluate these coefficients. And so far we have implemented the algorithm in Mathematica, and we're planning to, or we have started to implement it also in C++ to make the whole thing even a little faster. And yes, I guess I was a little fast, but this will be it. Thank you.
Thank you, Robin. Let's take 2 seconds to unmute ourselves and give a huge round of applause for Robin. So I see a few questions from the audience. Lorenzo?
Yes, hi, Robin.
Hey.
So I have a quick question, probably I just maybe missed something, but if you go to slide 37 where you showed the numerical evaluation, so is there a reason why you're not going above threshold? So there's no imaginary part here, you're only showing the real part.
Yes, I just, I was busy the last days and I didn't want to bother with doing the analytic continuation.
But it is possible, right? So there is no reason why you're not showing it here. Yeah,
no, of course you can.
Yeah, okay, thank you.
David?
Yes, my question is closely related to Lorenzo's. I point out that the original calculation by Bloch and Van Hove chose the modular parameterization so that tau I infinity, Q equals 0, was actually at the branch point. They expanded about the branch point. And in general, I think that we should be thinking of doing calculations, in Minkowski space, not in safe regimes where the amplitudes we're dealing with can have imaginary parts. And I wonder if your program can handle that.
Well, I mean, the program can essentially, I would say, handle any well-defined gamma tilde that you give us. Right.
So, for instance, on the top lip of the cut, you could handle it. There would be no problems. We wouldn't have to subscribe our own I epsilon to tell you what Riemann sheet you were on.
Well, that's the thing. So we assume that the integrals are well defined on the path of the integration. So if there's an ambiguity on which Riemann sheet you want to pick, then we have to specify this beforehand in some way. But I'm sure this can be done by preparing the EMP-outs accordingly.
Thank you.
Okay, in the time people think about other questions to ask, maybe I have a few quick questions about the speed. In particular, this part decomposition using lattice, how fast, how expensive is it? Is it like, what's the speed of?
I mean, this is essentially instant. So you mean this here,
Yeah.
right? No, this is pretty much instant because you can just, I believe already in Polylog tools, there is essentially an algorithm that does this for polylogs, but not too much changes here for elliptic polylogs. So the expensive step really is the expansion here. For example, maybe I should have, or I thought I put down the number here, but so here just doing all the steps 1 through 4 was a matter of seconds on all of the integrals. Mm-hmm. And then the expansion, so I expanded all appearing elliptic polylogs that are in my expression after I regularized them and decomposed the path. So I think they were around 700 EMPLs, and expanding all of them took about 25 minutes. And then evaluating the expression with in terms of polylogs took, I believe, about 10 minutes or so.
Okay, before I ask Stefan to ask his question, there is a comment from Claude.
Yeah, so maybe to comment on David and Lorenzo's question about the analytic continuation. And you can do that. So what is discussed here is just the evaluation of the elliptic polylogs. To analytically continue it, you would have to analytically continue essentially the homogeneous solution, which means tau, which means modular transformation on tau. So you know how the elliptic polylogs transform under modular transformation. You would get a different representation of the elliptic polylogs at a different value of tau, which you map back to the fundamental domain, just what you would do with the modular forms as well. And then in this transformation, you produce the imaginary parts, just like with modular forms. And then the whole thing starts again from there.
Yes, precisely.
So the analytic continuation step is in some sense decoupled from the question, how do you get the numerics if you have mapped all your points to a place where you know that you have a fast convergence series.
Yes, thank you, Claude.
Okay, Stefan, go ahead.
I have just a small question. You mentioned several times go back to step 1.
Yes.
I understand that, but my question is it clear that this procedure terminates always?
Yeah, so once you went back to, so step 1 and 2 essentially only act on the indices Z1 to Zk here and leave Z and tau invariant. So you just have to go back to step once every after step 3 and after step 5, and then afterwards you'll be done.
Okay.
Okay, if there are no more questions, we thank Robin again. Yeah, there's a room on Slack also with numerical evaluation. In case someone wants to ask there, please feel free to put your question there. Now we have a 45 minutes coffee break. Actually, now we have, we resume at 4:15 and see you all there. And I invite Pier Paolo to check his slides during the break.
Thank you.
Okay, so we can resume at 4:15.
Yes, and speaking of, it looks like most people have come back from the coffee break. There might still be a few more trickling in.